Alright, we have some special derivatives that we're going to be looking at here today, looking at transcendentals, so sine, cosine, and also the exponential and logarithmic functions. First off, we want to look at what exactly those functions look like when we draw them out. Sine and cosine waves go back and forth when you draw them. The main difference between them is that when you have sine, you go through the origin when you're waving back and forth. Cosine does not. It starts up at x equals 1 because cosine of 0 is 1. Okay, so those are the two main functions for sine and cosine. And as you can probably imagine, well, since the functions are so similar, that should mean their derivatives are similar as well. We'll get to that in a second. Now, e to the x and ln of x are inverses of each other. E to the x starts flat and then goes up forever. Ln of x begins going up forever and then flattening out. Well, as you can imagine, those are also going to be very similar derivatives when we deal with them because they are inverse functions. They should have something kind of in common. So first, the derivative of sine, just got to know it, it's going to be cosine. Just that easy. So the rate of change of sine is actually the cosine graph. So does that mean that the rate of change of the cosine graph is the sine graph? Well, not quite. It's actually pretty close. It's a negative sign. And you'll find out that any trig function that has a co with it is going to be a negative derivative value. Now, e to the x is a really cool idea. Remember that e is just a number kind of like pi. It's 2.71 something or other, goes on forever. But the reason that they do that is with this graph e to the x, it's actually more important than pi. No matter where you are, the slope, the rate of change that you have is always equal to the y value. The derivative is itself. It is its own derivative. It's always increasing at the same rate of which the graph already is, which is pretty cool. So since these are inverses, ln and e, that should mean that their slopes, if you remember from Algebra 2 and beyond, their slopes should just be reciprocals of each other. So no, it doesn't mean that we're 1 over e to the x because we flipped off your y and your x values. So really the way you write that is 1 over x. So basically whatever value you had in e to the x, the derivative stays the same. Whatever value you have with ln, it's not the same. It's the inverse of where you were with an x value. Okay, so those are the four that you just have to know. There's no real special trick or anything to it. You just need to know those derivatives. So let's take a look at some examples here and see if we can find the derivatives of all these, and we'll mix in some of our old stuff here as well. So this first one is we find f prime of x. Do each one on its own. The derivative of 8x to the third, well, we've done that. That's 24x squared. Minus 7x, this becomes minus 7. And the derivative of cosine, we said, has to be negative sine of x. The second one, g of x. So now we write g prime of x for our derivative equals the derivative of e to the x is itself e to the x. Keep it just like that. Minus 7 ln of x. Well, we'll keep the 7. ln of x becomes 1 over x. So 7 times 1 over x plus 2 times the derivative of sine of x is cosine of x. And the derivative of 3 becomes nothing. It just goes away. This part right here, I'm probably going to rewrite. Instead of having 7 times 1 over x, I can just rewrite that to be 7 on top over x. There's your derivative there. Number 3 here, we have y, so we're going to do y prime equals this first guy, the cubed root of x. Well, we don't like that. Let's rewrite that first. The cubed root, it's the power over the root. So there's the rewritten version. Make sure you still take a derivative of that. 1/3 x to the negative 2/3 power when you subtract 1 from your exponent. Now we have an exponential, e to the x. Its derivative is always just e to the x. So it stays the same. The derivative of negative 5 cosine. So keep the negative 5. The derivative of cosine, though, is positive sine. Or I'm sorry, the derivative of cosine is negative sine, so this becomes a positive 5 sine of x. And then the minus 1, again, is a number. It just goes away. Number 4 here. We have, again, a value that we're going to have to rewrite first. This 4 over x squared, to bring it to the top, I have to call it to the negative second power. So I'm going to rewrite this. I could call it y prime, or another way that they can write it is dy dx, means the derivative. So dy dx, when I bring that negative 2 out front, it now becomes negative 8. X to the negative third power, make sure you're subtracting 1 from each. The plus ln of x at the end is 1 over x for its derivative. That one was easy. This one right here is the tricky one they try to get you on. E cubed. This is not e to the x. This derivative is not e cubed, because it only happens when you have an x in that derivative. E is a number. If you cube it, it's still just a number. That means when you take a derivative, this part here becomes nothing. So your answer is really just negative 8x cubed plus 1 over x. If you want to rewrite it, negative 8 over x cubed plus 1 over x. That is fine as well. Okay, and this last problem is a fun one to deal with. Give you some room. If y equals sine of x, they want you to find the fourth derivative of y. So y is sine of x. I can take the derivative, y prime equals, we know the derivative of cosine, of sine is cosine. Well, that's fine. Now they want you to take another derivative. We call it y double prime. The derivative of cosine, we said, is negative sine of x. I can take a third derivative, y triple prime. The derivative of sine is cosine, so I got to keep the negative out in front though. Now they want us to do the fourth derivative, and they put this 4 in parentheses when you get really any more than 3 derivatives done. The fourth derivative of this value, meaning the derivative of cosine, well, the derivative of cosine is negative sine. But we already had the negative out in front, so that becomes a positive sine. Well, guess what? That's the exact same as the original. So that means that then if I were to take another derivative, the fifth derivative would be the same as our first derivative. So first, to answer the question, the fourth derivative of y fourth derivative, is equal to positive sine. What they'll probably do is they'll say not the fourth derivative, maybe they want the 40th derivative. Something like that. Well, we know it cycles. We know it's going in things of 4. So 1, 2, 3, 4, or first, second, third, fourth derivatives, 5th, 6th, 7th, 8th, 9, 10, 11, 12, and so on. And you can count up to any single value. So let's say, just for fun, the 46th derivative. That's a fun one. Well, if we're counting by 4s, we're going to get up to the 40th derivative would be right here. So the 31st would be the same as the first. And then 42nd, 43rd, 44th, and we'd cycle back up again to the 45th, 46th derivative would be this guy. So if it asks, for example, the 46th derivative would be negative sine of x. Okay, so that's just a way that you can see the cycling of some of these transcendental derivatives, especially with sine and cosine. The other fun one that I've seen done before is, okay, what is the 1,000th derivative of e to the x, and what's the 1,000th derivative of x to the 999th? Well, e to the x is always its own derivative, so that one's easy. It's going to keep being e to the x over and over and over and over again, no matter how many derivatives you take. The derivative of x to the 999th, well, the first derivative would be 999 x to the 998th. Then you would have to multiply 999 times 998, and it would be that huge number to the 997th. That would be the second derivative. You keep going over and over again. This exponent keeps getting smaller and smaller. Eventually we get down to just a number times x. So its derivative would be just that number. The derivative of a number becomes 0. So any polynomial like this eventually will get down to 0 if you take enough derivatives. So make sure you can see the patterns that form when you have transcendental derivatives versus just your straight polynomial ones like x to the 999th. So there's your transcendental derivatives.